As a first look at the solar system, we're going to compare planetary properties. You can see some nice pictures of the planets here. When we do this live in the classroom, I'll assign small groups of students a category, such as the mass, maybe a pair of students, and I'll have them list the planets in order of increasing or decreasing mass, one or the other, and then I'll have them look at their list and see if there's a place where it seems like there's a logical dividing line. And I'll have them do that with the diameters of the planets, their average densities, rotation periods, tilt of the orbit, and so forth. There are actually a couple of other categories that I've added to this that we'll look at. In several of the instances, Earth is used as the standard. For instance, we compare everything to Earth's mass, and so it'll be a multiple of Earth's mass or some decimal fraction of it. And same with the diameter, the rotation period, and the orbital period. All of those things we use Earth as the standard for. So let's see how these things come out. First category is the mass. No surprise here. Jupiter is by far the most massive of the planets. Jupiter actually accounts for about 0.10% of the mass in the solar system. The Sun accounts for 99.8%. Half of the remainder is Jupiter. Jupiter has more than twice the mass of all the rest of the planets, and so it's by far the most massive. But if we go down the list, then Saturn is only less than a third the mass of Jupiter, and then Neptune is less than a fourth that, or about a fifth that. Let's see, 50 times. Yeah, Neptune is only about a fifth the mass of Saturn. Uranus and Neptune are pretty close together, but when you go from Uranus to Earth, that's a 14.5 to 1 ratio. So that's the biggest leap by far that we've run across yet coming down this list. And so that appears to be a break. Earth and Venus are pretty close together in mass. Venus to Mars, though, that's an almost 8 to 1 ratio. And so that's a big drop there. Mars to Mercury, Mars is only about twice as massive as Mercury. But the biggest jump is going from Mercury to Pluto. Mercury is 27 times as massive as Pluto. If I was putting dividing lines in here, I'd definitely put a dividing line here between Uranus and Earth, and I'd put another one down here. There is such a big change between Mercury and Pluto that those two don't seem to be in the same category. Okay, then we look at the diameters. Things are pretty similar. Saturn and Jupiter are very close together in diameter, actually, which is surprising with that 3 to 1 mass ratio. Uranus to Saturn, Saturn's more than twice as large as Uranus. Uranus and Neptune are actually quite close together in size. The big drop here is going from Neptune to Earth. Neptune's nearly 4 times the diameter of Earth. And then Earth and Venus are nearly twins. Earth is twice as big as Mars, but that's not that big a jump. And then Mars and Mercury are similar. Mercury to Pluto, bit of a drop, but not like there was before. So I would probably just draw a single dividing line here and put it there. On to the next category, the average density. Density is mass per unit volume. Something that's dense is, say, a lead fishing weight. Lead is the most dense thing most people are familiar with. Actually, gold is more dense, but you don't usually see much quantity of gold. Lead is dense, styrofoam is not dense. The units here are grams per cubic centimeter. For comparison, water has a density of 1 gram per cubic centimeter. Look at Saturn down there. Its average density is less than that of water. And so that's kind of an interesting thing there. Earth turns out to be the most dense of the planets. Mercury is pretty darn close to Earth density-wise. Venus isn't far behind. A little bit of a drop down to Mars, but not a huge difference. From Mars to Pluto is a pretty good drop, and that's the most significant drop on this chart, is right here. It's interesting that Pluto fits in pretty well with these planets down here, although it doesn't really have much to do with them, but kind of interesting anyway. It's the difference in density between Jupiter and Saturn that accounts for the fact that Jupiter has more than 3 times the mass of Saturn, but it's not that much bigger than it, and it's because Jupiter is nearly twice as dense as Saturn happens to be. Okay, what else did we have? The rotation periods. These are interesting. The most massive planets we've got here, Jupiter, Saturn, Neptune, and Uranus, are the ones that turn fastest on their axes, and Jupiter is the one that spins fastest of all. It rotates in about 10 hours, so that's kind of interesting. Saturn isn't too far behind. Saturn, if you look at it through a telescope, you can actually see that it's a little bit fatter at the equator than it is at the poles, more so than any other planet, and that's because it spins so fast. Quite a drop, but not a huge drop. Actually, rotation period from Uranus to Neptune, or Uranus to Earth, these aren't quite so distinctive. Earth and Mars are nearly twins as far as rotation periods go. Pluto manages to sneak in there, turns on its axis in 6.387 days. Mercury and Venus are very interesting. They're actually strongly influenced by the gravitation of other bodies. Mercury turns on its axis 2 times for every 3 orbits that it completes around the sun. And so it's in a gravitational rotational resonance with the sun, with its orbit around the sun. And so that's what forces it to have the particular rotation period that it does. Venus has a rotational, for its rotational period, has a resonance with something else. It has a resonance with Earth. Every time Venus catches up to and passes Earth, it has the same face, or the same part of its surface pointing at the Earth. And so it's the gravitational influence of Earth that has determined the rotation period of Venus, which is very interesting. I didn't know that until last year. I read about that for the first time, and so keep learning. Okay, the tilt of the orbits. This maybe isn't quite so definite, and these are not that different for the most part. Most of the planets orbit in a plane or close to it. Uranus is the one that's pretty closest to Earth as being tilted the least, but Jupiter's not far behind, and neither are Neptune and Mars. 1.9 degrees, even up through Venus, 3.4 degrees, isn't that much of a tilt. Mercury, 7 degrees, that's a bit more extreme. It's twice as much as Venus, but Pluto's way out there by itself. So it's hard to definitely split this into 2 groups, but Pluto does seem to be in a class by itself. Just put a little bit of a dividing line here, but it's not real strong. The orbital period in years, well, maybe a little bit of a surprise. Mercury and Venus, not that far apart, I guess. I don't know. This has as much to do with distance from the sun as anything. Of course, Kepler's third law says that, but there is a big jump from Mars to Jupiter for the orbital period, and that's the biggest jump in here, I think. This is Jupiter's orbital period is more than 5 times that of Mars. In fact, I think it's close to 6. So probably there is the best place to divide this one. Saturn, almost 3 times as long as Jupiter. Saturn to Uranus, definitely 3 times as long. And then Uranus to Neptune is almost twice as long. And Pluto, not that much longer than Neptune. So, but still, between Mars and Jupiter, a definite dividing line. Number of moons, you can just look here. Some of them have 2 digits and some of them have 1 digit. That might be the most obvious place to divide it. Saturn up to 82 moons now. It actually has more than Jupiter. Jupiter's got 79. Many of the moons of Saturn and Jupiter are really small, though. You'd have even a hard time seeing them if you were in the Jovian or Saturn system without optical aid, so they can be tough to see. I suspect that if we ever had spacecraft that were orbiting Uranus and Neptune for long periods of time, we might discover more moons around them. We've had spacecraft orbiting Jupiter and Saturn, plus they're in closer to Earth, and so we've been able to discover some of the smaller moons of those. But for Uranus and Neptune, we've only had a single flyby of those two planets, and we haven't really had a chance to discover some of the little tiny moons that we have around Jupiter and Saturn. Pluto's got 5 moons. Little dinky Pluto. They're not very big, except its largest moon, Charon, or Charon, I've heard even, is the largest moon in relation to the thing it orbits of all of the things that used to be considered planets. Pluto isn't considered a planet anymore. Then we drop down. Mars has 2, Earth just 1, Mercury and Venus don't have moons. In a few million years, Mars will probably be down to 1 moon. One of its moons is on a decaying orbit and will probably be torn to shreds by the tidal forces from Mars at some point in the future, especially if it's not held together very tight, or it could just decay into the planet too and become a part of Mars itself. The semi-major axis, okay, this is another place where we can definitely divide things into 2 groups. If you look here, Mercury 0.39, Venus 0.72, almost twice as far out. Venus and Earth aren't that far apart. Earth to Mars, 50% farther. But then when you go from Mars out to Jupiter, you have to more than triple the distance between those two. And then look at these 4 top ones here. Mercury out to Mars, that's a gap of only about 1 point, let's see, altogether about 1.1 astronomical units, and all 4 of those fit into it pretty well. But then get past there, Jupiter 5.2. The gap out to Saturn is 4.3 astronomical units, and the gap from Saturn to Uranus is almost 10 astronomical units, and then another 10 to get out to Neptune. And so you can definitely say that Jupiter, Saturn, Uranus, and Neptune are very widely spaced compared to these inner 4 planets. So I'd put a dividing line here. Pluto seems to fit in okay with these, at least as far as its semi-major axis. With that very, well, we haven't looked at eccentricity yet. That's the next thing. This is a measure of how circular a planet's orbit is. The closer the number is to 0, the more circular its orbit. Venus's orbit is very nearly circular. We could draw one on the whiteboard and you wouldn't be able to tell the difference between that and a perfect circle. Neptune isn't far behind. Earth is not too far behind. If we drew Earth's orbit to the correct eccentricity on the whiteboard, you'd think it was a good circle too. As we go down here, they don't vary a huge amount until they're all less than 0.0 or 0.1, even Mars, which is the most eccentric of the bunch, till you get to Mercury, and it's more than twice as eccentric as Mars in its orbit. So, and then Pluto is more eccentric still. So hard to tell anything from the eccentricity. They're just nothing all that great on there. But we've done enough where we can actually split the planets into 2 categories, and we'll look at the distinctive characteristics in another video. But we would split them into these 2 groups. The terrestrial planets, that means Earth-like, and of course Earth is one of those. Nothing's more like Earth than Earth. And then Earth, Venus, Mars, and Mercury. And then the Jovian planets, which is an adjective that means Jupiter-like. So Jupiter, Saturn, Uranus, and Neptune. So those are the 2 major planetary groups. And then everything else in the solar system falls into different categories that we'll look at in another video.